Welcome to Engineering Innovations, the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering. I'm your host, Kristin Malavenda, Communications Director for the school. On this podcast, we explore cutting-edge research and groundbreaking ideas shaping the future of technology and engineering. Today, I'm excited to introduce our guest, Dr. Jenna DiVincenzo. She's an assistant professor here at Purdue ECE, and Jenna's work focuses on software verification. It's a critical process that ensures software behaves as intended, free from bugs or unexpected issues. And in this episode, we'll dive into the world of software verification and explore how Jenna's work could revolutionize the way we develop reliable software. Jenna, welcome to Engineering Innovations. It's great to have you here.
Awesome. Thank you. Thank you for the great introduction.
No problem. So let's start off by learning a little bit about your journey to where you are today. What led you to become a professor at Purdue and specialize in software verification?
Yeah, so it was kind of an interesting journey, I guess. So I was always a math geek. Since I was young. I think it was just the subject that I guess, like...
Gravitated?
Yes, gravitated is a great word.
Yes.
Gravitated to above the other ones. I think I like the puzzle aspect of math.
Yeah.
And then it was funny. I know some of my other colleagues in computer engineering always talk about like they grew up with computers and stuff too. I did as well. We did have like my dad was into like building them and we had them in the house. But he did like have computers there. Like we did like the like Jump Burst CD games.
Right. Yeah.
So like they were there for education, but like for me it was video games.
Gotcha.
So back then I guess the video games were like a little bit like less memory, not as fancy, not as great graphics, but it was I loved them.
Yeah.
So that's kind of how I got into computers, was by playing video games. And then but my high school didn't really have anything for programming or computer science or computer engineering, so I just, in school, I gravitated towards math.
Gotcha.
And so I was really fortunate in that I was definitely knew I wanted to go to, actually I went to the local university because of financial reasons and commuting cut back costs significantly. And so I kind of knew I wanted to do math because that was a subject in school that I thought was cool, and I was like, well, they have math at college, I'll do that too.
There you go.
So I was kind of always on the track of being a mathematician, which was kind of interesting. But my high school math teacher was like, there's a thing called computer science. Why don't you try that since you like both math and computers? So I did both in college, and I really liked both. And I think what ended up drawing me towards like research was like some really great faculty. And specifically, the faculty that I worked with were in computer science doing software engineering research.
Gotcha.
So the software engineering research, I was like, well, also I thought software engineering just, like, I did love my math, but I thought software engineering was so cool because maybe this is, like, the inherent engineer in me. I love seeing, like, the things that I typed out this code on a screen, and then it made something
Right,
work.
yeah.
So I thought that was like so cool, and there's a lot of like logic behind writing programs and thinking about how to build them correctly, so it kind of like meshed the two things I really liked.
Yeah.
And like I really couldn't get over the excitement of watching something work that I built.
That's great.
So I like the research was always geared towards the research I did in undergrad was always geared towards helping software developers and then in the domain of like software engineering. So I think that kind of was always an aspect I wanted to have going forward, was helping software developers build better code, better software. And I think so between my love of math and wanting to help software developers build better code, once I learned about this thing called software verification, I was hooked.
You're there. You were there.
That kind of like led to my journey of like what I wanted to do during my PhD.
So for people who aren't familiar, can you explain what software verification is and why it's so important, especially for things in modern day life like medical devices or car software?
Yeah, I think this is a great transition because I was just saying how I like software verification. It combines the math and logical thinking that I like, and the helping build better software that I really love. So software verification is this idea of, well, it's actually at its highest level, a very simple idea. You build code, very important code that might be like in a medical device tracking people's or like making sure people get the right dosage of medicine, for example. Or in airplanes,
that's important.
Very important. We have like what is it? The auto flight software.
Yeah.
Where like, lots of software that like pulls data from sensors and aggregates them so your pilot knows what's going on.
Right.
But also like the autopilot, which they use frequently.
Yeah.
All software, right? And you want that to be working, right?
Absolutely.
You want your medical device to be giving you the right dosage.
Yeah.
And knowing when to distribute that appropriately. And so in those cases, it's very clear you really want your software to be doing what it's supposed to be doing. You don't want it to crash or stop working
Right.
or do things that you didn't expect
Right.
it to do. And that, I mean, those are the critical situations, but you can also think in your phone, you have an app,
Yeah.
it crashes.
Right.
Probably because there's something wrong that
Yes.
someone who built that app didn't intend it to
Yeah.
do. So at a simple level, software verification is the idea of making sure your code that you built is doing what you want it to be doing.
Makes sense.
And so like diving a little bit deeper though, it's actually a mathematical proof that your code is doing what it's supposed to be doing.
Oh, okay.
So you can actually translate programs into like logics, and we work a lot with what's called a first order logic. So some of the students that may have taken discrete math have worked with that a lot. And you can also write what you want the software to do down in a mathematical logic.
Oh, okay.
And so the tools that I work with, they try to automate the process, which is like what you want.
Right.
Because not everyone and not all software developers want to write in logics or think about logics.
Yeah.
So you want to build tools that try to automate that process. But basically it takes that mathematical specification and it analyzes the code against that specification, but while it's analyzing it, it turns the code into big math formulas.
Gotcha.
And then it tries to prove that math formula is, well, we call it SAT or unsat, but it's really making sure that math formula is like true.
Right. So I can see how this is combining your
Yeah.
love of math and your love of computers as well. So you work on something though called gradual verification. What is that, and how does it differ from the usual ways of testing software and making sure it works right?
Yeah, so the idea of gradual verification, so it kind of originated from these two kind of camps of software verification. One camp is trying to prove that your code is correct with respect to the specification at compile time or statically, and so that's before you run the code. And so in that camp of tools, it turns out, the goal is your program actually, when it runs, so in programs there can be things called if statements.
Mhm.
So if you do one thing,
Then this happens.
Yes,
Yes.
if you do something else, another thing
Yeah.
happens. And so that's called like execution path, like a branching. So depending on what scenario that is, you go only down the one path, or when it's running, it could go down the other. It just depends on what condition it takes. So we call these execution paths, and there could be many, many, many in very large software systems. And so the idea of these tools at static compile time is for every execution path, you know that your code is correct with respect to your specification. Very strong guarantees, because you know, no matter what, no matter what other path your program takes at runtime, it's always going to be correct.
Right.
But to get those very strong guarantees, you just actually have to provide a lot of additional help to the tool. So that's kind of like the camp of static tools, and like I said, they work before runtime, so they don't get to utilize a lot of the information you get to know at runtime, and so it's kind of like the opposite of testing, and that you do it before runtime, and you get so much more stronger guarantees than testing. Whereas the other style of verification, which is very much more similar to testing, so it's at runtime. So you still write specifications of what you want your code to do, and they kind of provide these guards on your code. So when you're executing, if your code is getting to a place that violates these specifications, it stops. So it's a little bit stronger than testing, because testing, usually you come up with your own test cases where you're trying to, where you're more thinking of specific cases where things could go wrong, whereas when you think about the specifications you're writing, you kind of think about what is the overall behavior, and that kind of eliminates a lot of, instead of thinking okay, what could go wrong, it's okay, what do I want it to do? And then you guard against that at runtime. So they rely on inputs, both testing and dynamic verification. But you're thinking a little bit more abstractly and getting a little bit more stronger guarantees, because with testing you're usually just trying to find the bad cases.
Right.
But it's very similar in terms of, like, you need inputs. It only gives you guarantees on one execution path, because that's the execution path you're running. And so, and then there's a runtime cost associated with it. So those are kind of the pros in that is you actually don't need very strong specifications. You can kind of write what you want which is the benefit of testing and dynamic verification versus static verification. The user has a much more lightweight way of doing verification.
I gotcha.
And so gradual verification kind of is the idea of combining them and in a smooth way, so that you can the user gets to trade off between whether they want to do more work and get stronger guarantees, or if they want to do like less work in a piece of code and get less guarantees but still strong guarantees of progress on their code. And trade off between runtime costs versus not runtime costs.
Gotcha. So how did you come to focus on gradual verification? Was there a particular problem or gap in current software testing models that you wanted to solve?
Yes. So, so really I just wanted, people use, these very strong static verification tools in, critical software. And that's great, but the cost of that is very high.
Okay.
So they spend a long time really getting it right. I mean, we want them to be doing that right.
Right. Yes.
But the question is, one, can we branch out to just beyond critical software? Or if we have a critical piece of code, how can we make that process more efficient also? So the idea of gradual verification is to and we kind of explored, as we've been exploring this, we kind of figured this out, is giving testing it has a great way of giving you feedback on things you're doing.
Yeah.
Because it's very quick. You kind of just get really quick feedback on how things are going. Dynamic verification kind of does the same thing. It gives you many more details about the specifications you write, what your code's doing. Can't give you the strongest guarantees, but it's good iterative feedback that you can work very quickly on. Whereas static verification tools, they tend to be you really have to be an expert. You really have to know how, and even when you're an expert, things can you can get very confused on the steps in the static verification process. Really unsure about how you can change your specification to get the tool to work. And so, what can speed up that process is getting feedback not just on the static side, which is what people have to do now because that's all they have. But instead, okay, maybe you're stuck on the static specification and this critical piece of software. And so your goal is full static verification and specification of that code, but can you get some more feedback during that process so you can be more efficient getting to that full static verification? So allowing a user to switch basically to dynamic feedback and kind of get that feedback to give them more context that they didn't have before. So in critical software, I expect gradual verification to work more as a path towards full static verification, where you can start from nothing and get feedback all along the way, a very incremental feedback process, which existing tools that just do static verification can't give you.
Gotcha.
So they're very all or nothing. I'm giving a gradual ramp to full static verification. And then the cool thing is, critical software often exists in a context of non-critical software.
Right.
In a plane, you have the autopilot software, but you also have, and I'm sure I'm not really familiar with
You're not a pilot.
of plane software, but you also have software that just works the TV for all of the TVs on the plane. Right. So if that's not working, I mean that
people might get annoyed, but it's not a big deal.
Right. So I'm sure in some ways there are pieces of non-critical software that exist in the plane that interact in a very lightweight way with critical pieces of systems. So you want to do the work to get that full static verification in the critical systems. Right. Because you want those very strong guarantees. And you can do that more efficiently with gradual verification. But then you can still get some more lightweight guarantees on the non-critical parts. So testing, but also like a little bit stronger with dynamic verification.
Okay. So
it's kind of like being like actually allowing you to do more flexible testing across systems that you want to apply that to, and then like also getting the much more efficient benefits of static verification in those critical parts of the code.
makes sense. So when you're doing your research, are people coming to you with systems and they say, can you help make sure this works, or are you kind of working more theoretically? How do you go about testing these processes?
Yeah, so I mean, my work up until this point has been very theoretical. We're trying to figure out if we can even build a tool that can work with both static verification and dynamic verification, and also in a way that, like I said, is very like a smooth trade-off between the two. Well, fortunately, we've been able to do this for like your data structures and algorithm code. So like kind of extending bit by bit to like more fancy code.
Right.
So to this date, we're kind of just taking our baby steps, just like how code advanced. We're kind of like advancing along the path of like smaller programs to like more larger programs. So I have played around with some like compilers actually for programming languages, and we've been able to verify those. So honestly, just going out into the wild, there's a lot of open source code, and just seeing what we can do and where the gaps are, and then kind of expanding. But there's a lot of great industry partners out there with lots of interesting code. So as we get the tool to a certain baseline, I think I would love to explore more like industry partners that have code bases that we can keep pushing the boundaries.
Yeah.
There's a lot of cool verification competitions out there.
Oh, really?
Yeah, I'm actually organizing one of them this year, and we actually go to industry and ask for like
a problem that they
problems.
have. Yeah. Yeah.
So looking at those and some of the past ones would be, I think, a great way to kind of keep pushing gradual verification in the right direction.
So you have a project called, is it Gradual C0 or is that what it's, okay.
Well, Gradual C naught, Gradual C0, people call it both.
Gotcha. So that deals with complex containers for holding data in software programs. What makes handling this data so challenging?
Yeah, so I think some of the tricky parts, so for those listening, those kind of containers, I'm kind of talking about the ones you would see in data structures and algorithms, the ones that are actually core to a lot of systems in their libraries. So a lot of software systems utilize libraries, and those libraries have containers like lists. They have containers like arrays, they have containers like vectors, binary search trees, like lots of trees. So very core data structures that you want to know that they're working correctly.
Yeah.
That's kind of where we are right now with gradual verification, making sure those core data structures are working.
Gotcha.
They should be with gradual verification. And so what's challenging about those is, especially some of the like recursive ones, so like trees, lists, and graphs, you actually don't know how much data you're going to put into it. It can keep growing.
Right.
And it turns out, what's really interesting about these data structures is the way that you have to think about them from a static verification perspective is very different than the way you would treat it at runtime. So they have two different types of interpretations, statically versus dynamically.
Right.
And we have to marry those two in one working tool. So we've actually come across a lot of nuances in building and designing a tool that works for verifying and allows you to trade off between those two different checking mechanisms, but also which really we've actually introduced some bugs in our tool that we've had to fix later.
Right.
Fortunately, we're using some really cool mathematical techniques to model our tool and then like prove it also doesn't have bugs in it.
Right.
And that's really what helped us find this bug. But it turns out those really different interpretations of how you would check these data structures at compile time versus runtime, that interaction is very nuanced, and it's very easy to design it in a way that doesn't actually has bugs in it.
Right.
So we have bugs in our tool, which is not good.
Right. So you use a method called symbolic execution in your approach. What is that, and why did you choose this method?
Yeah, so symbolic executions are actually a pretty cool technique. It's actually used a lot in all kinds of different static analysis tools. So the static analysis tools I work on are like very strong. They do like a ton of things. But there's also more lighter weight static analysis approaches, and some of those that you even use symbolic execution too. So it's mostly a static technique, and the reason why it's a static technique is it's actually modeling how the program executes statically. So you kind of make abstractions on, so as a program executes, there are variables, and those variables hold values, and at runtime you can actually get the concrete values. But statically, you don't know all the time, depending on what your program looks like, especially complex code, what those variables hold in them, and you can't see that until runtime.
Okay.
So you kind of basically replace those values with, or like your own symbolic value.
Okay.
Which is kind of just a variable.
Yeah.
Another variable. And you basically symbolic execution executes the program like it would at runtime. Same flow, but instead of evaluating down to like one, like an integer, like 1 or 2.
Yep.
It has this like, we kind of call them alpha and beta as a good example, just kind of like an abstract value that represents what the concrete value should be, and then you can like model the execution of the program from them.
Okay.
So I don't know, I think it's a super cool,
like
it's like a very slick technique that someone much smarter than I came up with a long time ago. But it turns out it's super great for doing static analysis on things and doing it efficiently.
Okay.
Because not only do you want, so you definitely want things to be fast at runtime, but you still want them to be fast at compile time. You don't want people don't want to wait for their tool to work for a long time, right? They don't want to wait minutes or hours. So you want that to be efficient as well. Symbolic execution is a great way to do static analysis very efficiently, which is one of the reasons why we also want our tool to be based on it. But it also just turns out, because of the efficiency, a lot of static verification tools are built with symbolic execution, and so our goal was we want to build on top of those. We want to actually, one of the research directions I'm really interested in, I think we've done an okay job of it so far, but I really want to make it a lot easier for people, because there's so many different static verification tools out there. I want to like make it easier for them to be able to build Gradual tools, because we know they work.
Right.
They make life a lot easier.
Yep.
So how can we like make it easier for? So we've built on top of an existing tool that we liked, which has symbolic execution. But like, how can we do that more generally? So like, other people with other tools can build the same Gradual system.
Yeah.
So taking a look at symbolic execution was really important for us, was because so many tools use it.
Gotcha. That makes sense. So one goal of this Gradual C0 is to reduce the number of checks that you need while the software is running. And I guess if you have fewer checks, then it runs faster. Is that the idea?
Yeah. You got that exactly right. So because we're changing, like basically our tool is allowing you to trade off at any point, pretty much at any level of granularity between static and dynamic checking. If you can check something statically, we don't want to check it at runtime because that's just doing extra work and slowing down your program to do work that we've already done, right? So the idea of Gradual C0 and a big actually challenge when we were implementing the tool is how do we leverage as much static information as we can to then reduce the runtime checks that it has to produce. Because, again, if we check it statically, there's no need to check it at runtime.
Right, and everybody wants things to move faster, faster. So this is also the first tool of its kind for handling complex containers for holding data in software. What were some of the biggest challenges you faced in building it and are still facing, and how did you overcome those challenges?
Yeah, I touched on it a little bit. Definitely the nuances. So not just the recursive data structures. Not only do they have different interpretations or ways to reason about them statically versus checking them at runtime, there are like lots of other techniques that have the same issue, where you would treat them differently statically versus how you treat them dynamically. So that'll always consistently, I think, be a challenge in this work, is how do you marry them together in a way that's sound and also useful, aka gives you a good trade-off between the two. And then, so that's always going to be a challenge. I think another challenge is runtime.
Yeah.
So, like you said, things want to go, we need to move things fast. We want to make things go fast. But some of this, so to make sure our tool is what we call sound, means it catches all the bugs in your code. So soundness means we will catch like if there is an inconsistency between what you want the code to do and what's actually doing, we'll catch that.
You're going to find it, yeah.
Yeah, very strong guarantee we need to make sure our tool has. And so to do that, whatever we assume statically, so we do it kind of like what we say an optimistic static thing. So if you're missing information, but we need it to do like a static proof, we say, hey, we'll just assume this is true as long as it's clearly like okay to assume this.
Right.
And then we'll check it at runtime. So that's kind of like how our trade-off works. And so this assumption has to be checked at runtime because we don't know whether it's true or not, and we can't know that at static like compile time. So we have to check it at runtime. Now, what's challenging about this is some of the things you want to check statically are not things that we've thought about checking at runtime.
Oh, okay.
And so, depending on what your static system has in it, it could, it's very hard to make these checks very fast.
Gotcha.
So, really thinking about, like, in ways that no one has thought about before, because no one's tried to combine these in this kind of way.
Right.
So, there's, like, a lot of interesting, like, static verification things you want to write. How do we check those at runtime efficiently? That's something that no one's explored before, and so we're trying to figure that out. And the more we extend a different code, the more we have to figure it out. It's going to continue to be a challenge, especially the more we go to different domains.
Right. So when you do your research, I'm sure it involves working with others. What are some of the collaborations or partnerships that help you with your research?
Yeah, so I think this is maybe a different answer than most people would say for this question, but I think my favorite collaborations would be just with students, like undergrads.
Yeah.
So I love working with undergrads. I love so I love my PhD students, of course.
Mm-hmm.
Like that's the traditional. They're so fun to work with as well. But like working with undergrads, I guess it wouldn't be a collaboration, but it's just like so fun. I think because it's fun to watch them grow. And grow in a short time. I guess that's what I love about mentoring PhD students. You can really see them grow over a long period of time. But it's so impressive. I also think Purdue EC has some really great undergrads I've worked with so far since I've been here. But it's so cool to see them kind of like, and I like when I work with undergrads, I like them to do something like cool. Yeah. Like not just
to get them excited, yeah.
Yeah. So it's so cool to like watch them over, because I usually try to work with students for multiple semesters. Over those semesters, just like jump in, kind of figure something out, do something like smaller, say in the summer, and then like learn so much from that they really do something like long term, really cool in the research. So those have been the most rewarding collaborations.
Yeah, I can see that.
And honestly, the tool that we built, that Gradual CNOT tool, that tool has been built by like 5 undergrads.
Oh, that's great.
And like, so obviously I overseen like all the different pods working on the different pieces, but in general, like undergrads built that tool.
Yeah. So more and more undergrads in various disciplines are doing research as undergrads. And I think in the past it was undergrad was kind of book learning, and then you did research when you went into your graduate school program. How has that changed over the years, and do students come into you kind of knowing more about computers and software maybe than they would have in the past, or they're all starting kind of from the same spot?
So I think, well, in terms of what I do, I don't think it's a rare student that gets a chance to do work related to what I'm doing. I think Purdue is really nice in that we have a lot of like really great courses that are like expansive. So they do, the ones I've worked at Purdue do come with a really like solid computer science, computer engineering background and math background. Yeah. I was actually very impressed. Our discrete math class that teaches them core concept for the kind of work that I do. They'll have to learn more, of course, but I think that they come very prepared to work with me, and especially so that's been very impressive. And though there's like a lot of learning that happens, it's a transition to, honestly, it's a transition for me. It was a transition for anyone from thinking of like with research, there is no answer sheet.
Right. Yeah. Which can be frustrating, but also exciting.
Rewarding. Very rewarding, especially, like, so there's nothing set in stone. There's only, like, like things we've learned from experience that I can
then you help you set directions. Yeah.
But there's no right answer. I can like review it and say, okay, this looks okay.
Right.
But they kind of have to like struggle through that. I don't think anyone comes prepared to do that until they're actually doing it.
Yeah.
In terms of technical background, I feel like I feel like when I worked with, to be honest, I worked with undergrads at CMU. And I worked at undergrads at Purdue, and these are the top computer engineering, computer science students.
Right.
So a lot of them have very solid backgrounds, and even at the sophomore, like early levels, very strong backgrounds. So I don't really have the context to know if that's changing.
Yeah.
In terms of going into PhD programs, I do think that there is, fortunately and an unfortunate, push towards undergrads having more research experience. But I think the good places are pushing back a little on that. At least I do when I look for PhD students. I want them to have taken coursework where they show that they would be interested and like capable in the work that I do, but they don't have to necessarily have done it or published papers.
Right.
I think a lot of faculty are like that. So when, at least from what I've talked to at Purdue and elsewhere, is we want you to at least done some research experience, so you know that you like research, that you can handle it. That's a thing that you would want to do long term, because when you're in a PhD, it's a long road. So we want to eliminate that risk by making sure you did something. Yep. But you don't have to have research output. You just have to have done something cool and know that you like it and have shown that you were in some way successful, but that's. But
you have the skills to just to move forward in that.
And not afraid to move forward. Right. Perseverance, not, like, again, this is not something that you have an answer sheet to. Yeah. You kind of have to, and you're not afraid to fail. Research is a lot about failing. Yes.
Well, how do you help your students, whether undergrad or PhD, learn that failure isn't a bad thing or to hang their head? How do you teach them to move around these challenges?
Well, the biggest thing is I'm kind of honest about my own experiences, all my failures.
Yeah.
Like, and I think it's a good example. It's like, I'm here as a faculty in front of you, and your colleagues as well, like my colleagues as well. Like, we're here, but despite we've had all these failures.
Yeah.
So, like, actually, the Gradual paper just getting published. It's been rejected 3 or 4 times.
Yep.
It's a great paper now because of all of the experience, and now people are so excited about it.
Right.
But that's rejection. Rejection.
Yeah.
So very honest about that. Very honest about the process all the way through, like, in terms of like getting output from your research, say publications or something. Very subjective processes. Just being very open. I think, like, one thing I think has worked so well with my students and preparing them for, like, setbacks is just being transparent about the process of research from all aspects. Like, also being transparent about what my day-to-day, like, work and the things that I'm thinking about when I'm thinking about research. So just being really open with that.
Yeah.
And I think they enjoy it. I hope so.
Well, I would think that if your advisor said, well, I failed at this, and this too, that would make you feel better.
Yeah.
So when you're not researching or teaching or mentoring, how do you like to spend your free time? Do you have any hobbies or interests that help you unwind?
Video games.
Oh, okay. What do you play these days? I still
play video games a lot. So these days, so actually I just got done playing Fortnite a little bit last night.
Okay.
So I like to play Zero Build, but I also play Lego Fortnite. I like to build things.
Yeah.
I like to build things in games, just like I like to build software.
Yep.
And then I do like MMORPGs, so I've been playing Final Fantasy 14 online, which has been fun. And then I kind of recently got back into RuneScape. It was something I played as a middle schooler.
Right.
And then I guess it's still around and people still like it, so I jumped back in. That was kind of fun.
That's cool.
But yeah, right now I'm a little bit more into Fortnite. I have a battle pass going, so
I don't even know what that is.
Students watching might
yes,
know
I'm
what
sure.
I mean.
I'm sure.
Yeah, but so I gotta take advantage of the battle pass I'm paying for.
Oh, I gotcha.
Yeah, it basically encourages you to play because you spend money to buy it.
Right. That
you
makes
get
sense.
rewards, so it's fun.
That's great.
But yeah, so playing that, I kind of rotate. So
yeah, cool. So that brings us to the end of today's episode of Engineering Innovations, and I want to give a big thank you to Dr. Jenna DiVincenzo for sharing her fascinating work on gradual verification and giving us a glimpse into the future of safer, more reliable software. Thanks so much for being here today, Jenna.
Thank you.
If you enjoyed this conversation, make sure to check out some of our previous episodes. You'll find deep dives into everything from cutting-edge AI research to advancements in semiconductor technology. We've had other incredible guests from Purdue ECE who are leading the way in their fields, and you won't want to miss their stories. Don't forget to check the show notes for links to Purdue ECE's social media and website. Give us a like, give us a review. And it's a great way to stay up to date with the latest innovations and events happening here at Purdue. Thanks so much for tuning in, and I'll be back next month with another new episode of Engineering Innovations.